Yes. Okay.
Okay. Yes. So today we're very happy to have Anna Maria Raclariu from Perimeter Institute to tell us about celestial holography. Okay. Floor is yours.
Thank you very much, Victor, for the introduction and the invitation. I'm very happy to be here and get to tell you a bit about my recent work with Nima Kani-Hamed, Monica Pate, Andy Strominger, as well as Alex Atanasov and Walker Melton. So let me start off by saying that in physics, we are used to the idea that a physical theory is determined by its observables. And so if we want to understand quantum gravity, by which in this talk, I'm going to mean any theory that looks like Einstein general relativity at long distances, a natural question to ask is what are the fundamental observables and how do we compute them? Now, in practice, one answer to this question is provided by effective field theory, which is the idea that physical observables are actually organized by scale. And so for all practical purposes, our experimental energy scale is always going to be much, much smaller than the Planck scale, in which case one can do physics as usual and sort of characterize the theory by its scattering amplitudes. So for example, if one considers something like a process which is well approximated by a 2-to-2 scattering process, the scattering amplitude it can be computed as an expansion in some small parameter, which in gravity is going to be g Newton, with some coefficients, these ARMs here, which are both perturbatively calculable, and they encode information about any sort of interesting observable. So for example, they can be used, so these guys and their higher point analogs can be actually used to infer information about things like scattering angles or radiation emitted in such a scattering process. Okay, however, if we want to have a theory of quantum gravity, of course, we would be also interested in higher energy scales. At least in theory, we'd want to know, for example, what happens if our physical energy scale becomes very close to the Planck scale or larger than that. So in this case, from qualitative arguments, if, for example, one considers a 2-to-2 scattering process, where one, say, keeps the impact parameter fixed and increases the center of mass energy to higher and higher values, ultimately, what's going to happen is that we're trying to pack more and more energy in a fixed region of space-time. And if gravity is turned on, naturally a black hole is going to form. And not only this is going to happen, but if we also wait for a very long time, this black hole is going to evaporate. And so these effective field theory techniques, of course, I was talking about earlier, will break down. So in such a regime, we actually don't have a good quantitative understanding of what's happening, despite the fact that there are some qualitative features of such scattering processes, which I'm going to touch on later. Now, on the other hand, an answer to this question about what the observables are seems to be nicely provided by holography. So in ADS quantum gravity, holography is the idea that gravity in a bulk region of space-time is actually completely captured by a non-gravitational theory living on the boundary. So in particular, this non-gravitational theory is a conformal field theory. And the answer to our original question is actually provided by this non-gravitational quantum field theory supposed to be dual to this bulk quantum theory of gravity. And in particular, what we want to know is that these observables are actually just correlation functions in this conformal field theory. And so properties of these correlation functions, such as the transformation properties under symmetries, such as conformal symmetry, as well as unitarity and crossing symmetry, actually encode bulk properties related to these. So for example, unitarity, locality, and causality, they have imprints in features of these conformal correlation functions. And of course, in the past decades, this holographic duality has provided many insights into gravity, so far too many to be even mentioned here on this slide. Now, one could ask the analog question in asymptotically flat gravity. And there is one reason to believe that perhaps holography should also be the answer to this question in this case. And one reason to believe that is that black hole entropy universally scales as the area. So this is a relationship that holds in any sort of background. So in particular, asymptotically ADS gravity should be nothing special in this respect. However, there are a lot of qualitative differences to our previously described ADS situation. So one of the main differences in the two cases is that the boundaries are very different. So in the asymptotically flat spacetime case, the boundary, as we see here, is a null surface. And one naive obstacle is the fact that it's pretty difficult to actually formulate a local quantum field theory on such a background. Now, another major difference between the two situations is the fact that the boundary conditions one imposes in the two cases are fundamentally different. So here, these past and future null boundaries called scri minus and scri plus are actually Cauchy surfaces. And so if one specifies, for example, data at scri minus, the data at scri plus is actually going to be related to the data at scri minus by the S matrix. And even if one would try to formulate holography just on one of these boundaries, one would still run into the problem that the data itself at scri minus, for example, is actually constrained. So we have these constraint equations which lead to all sorts of subtleties.
So, sorry, can I ask a basic question since
yes.
you're generally motivating things?
Yes.
I mean, there was some effort that went into light cone gauge gravity and field theory and even string theory. Does that not? It's true that the Hamiltonian is complicated, but does that help?
Yeah, that is a very good question. I think some people, like for example, there's been some ideas with Raju Venugopalan at Brookhaven. So he was interested in these light cone sort of gauge ideas you're mentioning, but I would say that, yeah, they haven't really been explored very much. We thought about it a little bit a couple of years ago, but sort of didn't make much progress. But I do agree that I think that people should think a bit more about that. And I should also say that actually people, so there is this work by sorry, the name escapes now, but there is all of this story about trying to formulate a dual to asymptotically flat spacetime on these null surfaces. So having to do with these non-relativistic quantum field theories, which one can define on these null surfaces. And again, I mean, there is a whole story with these Carolian field theories and so on. So that may also be perhaps related to what you're saying.
Okay, thank you.
Yeah, thank you. Okay, so right. So another fundamental difference is the fact that here the boundary in this case is actually leaky. So there is radiation which can escape through scri, implies that it's quite difficult to, or quite subtle to define conserved quantities in this case. And the seminal work by Lee, Ayerwald, and Zupas actually provided a way to define conserved quantities in asymptotically flat gravity in particular, in certain situations under certain conditions. Now, another, and lastly, the last thing I want to mention is the fact that it's well known since the 60s that the asymptotic symmetry group of asymptotically flat spacetimes is actually not just the Poincare group, as one might naively expect, but it's actually an infinite dimensional in extension of that, which in particular includes angle-dependent translations of points on these cross sections at null infinity in the null direction. So these are called supertranslations. And for a long time, they were thought of as being a bug rather than a feature, because they made the definition of the scattering problem in this context quite difficult. So the reason why that is that if one specifies, again, a state on scri minus, the state on scri plus is going to be determined by S matrix evolution only up to a supertranslation. Now, remarkably, less than 10 years ago, this ambiguity was actually fixed by Strominger's insight that there exists a set of matching conditions which one can impose. And these matching conditions, their role is to actually identify the BMS minus group or a diagonal subgroup of this BMS minus times BMS plus groups, which a priori act independently on scri minus and scri plus, which then allows for the scattering problem to be well defined. In particular, this antipodal matching condition, the way it works is that, first of all, one can observe that gravitational data actually obeys this matching condition from explicit calculation. And then one imposes an additional such antipodal matching condition on the symmetry parameter. So here it's a function on the sphere, which parametrizes these supertranslations. And upon imposing this matching condition, one arrives at the relationship between the charges defined essentially at the past and future boundaries of scri plus and scri minus respectively. So we have this equality that the charges across spatial infinity are actually equal. Now one can extend these charges to actually lie on full scri minus and scri plus, which essentially amounts to the statement that there is a conservation law. So we have a symmetry and imposing actually that the symmetry commutes with the S matrix leads to a non-trivial interesting constraint. So, okay, the surprising fact was, though, that imposing this conservation law, the S matrix, turned out to be actually nothing but the soft graviton theorem. So what is the soft graviton theorem? So this is, again, an old idea by Weinberg from the 60s again, which relates a scattering amplitude with a low energy graviton to the same scattering amplitude without the graviton. So in particular, in the limit as, so here this yellow line, say, is a graviton of momentum Q. And as one takes the energy of this graviton to go to 0, this amplitude factorizes into a piece which is just the scattering amplitude in the absence of this graviton times a prefactor. This prefactor is actually universal, but one of its features is the fact that it develops a pole in the limit as this energy goes to 0. And these dot-to-dot corrections here are actually important because they determine the so-called subleading, sub-subleading, and so on theorems. So in other words, one can think about the right-hand side of this equation as an expansion in powers of essentially this low energy, or this Q variable, where the leading term blows up as Q goes to 0, the subleading term is order 1, and so on and so forth. So because of this tower of soft theorems, a natural question that arises is what are they associated with? Are they also associated with a symmetry? And the answer turns out to be yes. So the subleading soft theorem actually turns out to imply another infinite dimensional symmetry of the S matrix, which turns out to be, in fact, an infinite dimensional enhancement of Lorentz symmetry. So this is by analogy with these Supertranslations, which were just an infinite dimensional enhancement of translational symmetry.
So, sorry, Anna, is this statement just 4-dimensional, or is that 4 dimensions?
Yes, sorry, this is a great question. I should have said that I'm talking about 4 dimensions here, and this is, I'm also restricting. So for the leading soft theorems, it doesn't matter whether you're tree level or in the full quantum theory, but for the subleading soft theorem, this is a statement that is exact at tree level, and there's actually corrections, one loop exact corrections to this statement, which are not fully understood. But yes, I'm talking about 4-dimensional. I should say that I'm talking about 4-dimensional asymptotically flat spacetimes in this case.
But subleading soft theorems, they exist in any
that's right. Yes, this is a great question, but you see, there are even for the BMS, for the standard BMS, not its infinite dimensional extension, including this infinite dimensional generalization of the Lorentz symmetries. In higher dimensions, it is known that actually to leading order, this BMS group is actually reduces to just Poincare. But having said that, I mean, this was an original puzzle. If you try to study these things in higher dimensions, there seems to be a tension between the fact that the symmetries seem to collapse to just Poincare and the existence of actually, both leading and subleading soft theorems. And at leading order, we now understand that actually what happens is that one has to go to a subleading order in a 1/r expansion. So actually the so-called, the memory effect, which is, again, it's something I'm not going to really be talking about today, but it's related to this triangle of equivalences. So this diffeomorphism, these supertranslations act at the subleading order to the radiative order. And so naively, they're associated to charges that vanish. So it's no inconsistency with the standard statement that the BMS group is actually, if you just look at finite distance, it's Poincare, but nevertheless they are relevant because they do. One can indeed show that they actually imply these leading soft theorems. However, for the subleading orders, the problem has not been really studied that much, but perhaps a similar analysis can be done there. But I agree, yeah, only the 4-dimensional. In fact, in 4 dimensions, it's expected that this happens because the Lorentz symmetry acts as the global conformal group on the sphere, and we expect this infinite dimensional enhancement. But in higher dimensions, one wouldn't get the same thing. But nevertheless, yes, it would be very interesting to explore the connection to subleading soft theorems in that case.
Good, thanks.
Just a terminology question. So the BMS refers to just the group with the supertranslations and not the rotations?
Yes, that is right. The BMS refers to just supertranslations, that's right. And extended BMS, there is still debate on what the extended BMS group is supposed to be. So it may include these Virasoro symmetries. Some other groups claim that in fact it's even larger, so it includes all diffeomorphisms of the sphere. But it's a bit subtle because these were originally sort of thrown out from the get-go because they have these singularities at isolated points on the sphere. And they also don't really, they sort of map you out of the phase space as well. So they were a bit more subtle in the original BMS analysis. They were sort of not really studied. So Barnich and Trosser have actually discussed this extended BMS symmetries shortly before Andy's I guess Andy and Freddy Cacciazzo. There are many references here, I should say, that I'm missing. By now there is a lot of literature on the subject, but there's been some work by Freddy Cacciazzo and Andy Strominger where they discuss the subleading soft theorems, and then this work actually connected this Barnich work on this extended BMS algebra with this work on the subleading soft graviton theorem. So even the subleading soft graviton theorem actually was only proven at tree level in full generality as of 2014. So this is something which wasn't understood like a very long time ago.
Okay, thanks.
Okay, so I'm happy to take any more questions anytime, so just let me know. I'm also going to pause at various points. Okay, so we have this infinite dimensional enhancement of Lorentz symmetry, and in particular, one also can use this subleading soft graviton theorem to construct an operator, which is actually just a particular mode of the subleading soft graviton. So it's some sort of boundary graviton, whose insertions in the S matrix behaves like the stress tensor of a two-dimensional conformal field theory. So this, on the one hand, it's surprising. On the other hand, it's not so surprising because, as I said, the Lorentz group at infinity on cross sections on these celestial spheres, it acts as just it acts as SL2C, which is the global conformal group on the sphere. And so this infinite dimensional enhancement from a boundary point of view is sort of expected, because we know that two-dimensional conformal symmetry actually gets enhanced to Virasoro. But what's surprising is that this is a statement about gravity in four-dimensional asymptotically flat space. So it has this this bulk kind of avatar through the subleading soft theorems. Now, if you look at this equation, and there is one puzzling feature, namely the fact that the would-be weights. So these HIs in usual conformal field theory would just be numbers, and that they would be given by sums and differences of the spin and the dimension of the operators in the conformal field theory. Now here, this is just a statement derived from a bulk point of view, but these would-be weights are actually operators. And so they involve, instead of having a dimension, here one has this sort of scaling-like generator with respect to the energies of these other external insertions. And so natural question arises, namely, can we find a basis in which this operator is diagonalized? Now, the usual basis in which the S matrix is evaluated is a basis of energy momentum eigenstates, as we all know. And that actually leads to scattering amplitudes, usual scattering amplitudes, which generically won't diagonalize this operator. And this can be seen because, you know, at low energies, these objects are just polynomials in these omega i's, and those clearly will not diagonalize this operator. However, there is a way to get some objects which actually do diagonalize these operators. And
these OIs inside the correlations, how's the Z related to the momentum?
Yes. So yes. So here I should. That's right. So so by this correlation function of O1 ... I should say that I mean just the S matrix, which is a function of n on-shell momenta. Now, each on-shell momentum is parametrized by 3 variables. For a massless a massless momentum is always going to be parametrized by an energy and 2 angles. And these Z and Z bar variables are stereographic coordinates on the sphere. Essentially, like the momentum, I should have written it down explicitly here, but it's just energy and then one, and then a vector which is normal to a point on the sphere. Yeah. And that normal to the sphere can be essentially expressed in terms of these Z and Z bar variables. So naturally, a scattering amplitude of n massless particles is already labeled by points on the celestial sphere, up to the fact that annoyingly we have these operators actually being functions of energy. So how do we make the scattering amplitude into an object that actually just lives on the celestial sphere itself? Well, it turns out that one can take a so-called Mellin transform with respect to the energy of these external particles. So again, I'm just talking about the purely massless scattering case. So an asymptotic particle state, which, as I said, is labeled by an energy and two angles, can be traded into a momentum eigenstate, which is now labeled by a scaling dimension and the same point and the same point on the sphere by this integral transform. So this is just a logarithmic Fourier transform, and it can be shown that what it does is to turn a momentum eigenstate into a boost eigenstate. So by boost eigenstate, I mean, so which boosts? I'm talking about boosts in the directions of each of these external particles. And so this leads us to the idea of celestial amplitudes as nothing but S matrices expressed in a different basis, namely in a basis of boost eigenstates. So these are the objects we're going to be interested in today. And let me, before going to the outline, let me just flash a couple of the properties we understood in the past couple of years. So one of them is that celestial amplitudes obey a wide range of symmetries. And the most basic symmetry they obey is Lorentz symmetry, which is actually just manifest as SL2C covariance. So these celestial amplitudes, by construction, they transform as correlation functions of primary operators in a conformal field theory. Now, this is nice, but we get this nice property at the expense of having a less natural transformation property under translations. So what can be shown is that actually the way translations act on celestial amplitudes is by shifting the dimensions of these operators. And in particular, momentum conservation now becomes a non-trivial relation between celestial amplitudes with involving operators with shifted dimensions. Now, there is a whole range of other symmetries, and indeed we don't even fully understand what the full symmetries are of gravity in four-dimensional asymptotically flat spacetimes, but we know for sure that there is a tower of soft symmetries, and this has been discussed in a series of very recent works. And they were shown to have a very interesting algebra. But in particular, the subleading and sub-subleading soft gluon and soft graviton theorems were actually shown a bit earlier to imply non-trivial constraints on celestial data. So by celestial data here, an example would be the leading or subleading behavior of the celestial amplitudes in a collinear limit, which is essentially characterized by an OP coefficient, just as in usual conformal field theory. So the statement here is that these OP coefficients are actually fully determined, the leading and subleading ones, and in more recent work, there are statements about other ones as well. They are constrained by these soft symmetries. Okay, now you may ask, okay, we have this reformulation of gravity in terms of a theory that lives on the sphere. And a natural question is, okay, what can we learn from this dual description? And the answer is that so far we don't really know, but there is evidence that perhaps we could learn something interesting and non-trivial from this. And so today I'm going to provide a little bit of evidence in favor of a positive answer to this question by just studying celestial 4-point scattering of massless scalars. So it turns out that these 4-point amplitudes, just like in conformal field theory, they encode a lot of interesting information about the theory. And it's natural to ask, general properties about what their structure is and how this structure actually encodes information about bulk scattering. And just like the 4-point amplitude in momentum space is a function of two variables, namely the center of mass energy and the momentum transfer, we will see in a moment that celestial amplitudes are actually functions of a parameter, which turns out to be related to the sum of these external dimensions of these 4 operators, and a conformally invariant cross ratio. So the sum of the external dimensions is a Mellin dual to the center of mass energy, while the conformal cross ratio is just the ratio between the momentum transfer and the center of mass energy in the bulk. And we'll see that the analytic structure in this first variable, in this complex boost weight plane, captures both perturbative and non-perturbative aspects of bulk scattering. So this is going to be the first part of my talk. And in the second part of my talk, I'm going to study the analytic structure in this second variable in the complex, well, in this cross ratio plane. We're going to see that one can perform a conformal block decomposition of certain celestial amplitudes and extract information about the spectrum and the OP coefficients from that, just like one would in usual conformal field theory. So before I move on, so here is a slide about the structure of massless scalar 4-point scattering. So from a bulk point of view, we know that a 4-point amplitude is characterized by a function of 2 Lorentz invariants, S and T, up to this momentum conserving delta function. So this is just basically fixed by Poincaré invariance. And I'm taking the center of mass energy to be the sum of P1 and P2 squared, and the momentum transfer to be a sum of P1 and P3 squared. And upon using these parametrizations in terms of these points on the sphere of these massless momenta, one can show that the ratio of T and S is actually a conformal invariant Z on the sphere. So this is just by explicit calculation, one can see that, which then naturally leads us to a formula for the associated, for the general celestial 4-point function. So the general structure is that the celestial amplitude in this case is going to be proportional, first of all, to just one Mellin transform with respect to the center of mass energy, essentially, where the Mellin dual is this beta variable, which turns out to be the sum of the external dimensions of these operators. So how does this come about? Well, it's not hard actually to see that here we have 4 constraints coming from momentum conservation. And we also have 4 Mellin integrals, right, associated with Mellin transforming with respect to the energies of the 4 external particles. So the way one just ends up with 1 Mellin integral as opposed to 4 is because 3 of these momentum conservation constraints actually get immediately saturated by 3 of those integrals. And at the end of the day, one just ends up with one integral over this scattering amplitude, over this stripped scattering amplitude. Okay, and then this prefactor here consists of 2 pieces. One of them is a conformally covariant prefactor, which one could have guessed by conformal covariance to begin with. And then there is this other function of the cross ratio, which is proportional to this finite delta function, which enforces the reality of the cross ratio. But this again is nothing but a consequence of bulk momentum conservation. So this is just coming from the statement that 4-point scattering actually happens in the plane. And so at the points at which these 4 particles are going to cross the celestial sphere can always be put using conformal symmetry on the equator, let's say. So this is just a statement that momentum is conserved, and this other function is actually universal. It can be just computed. It comes out of this explicit doing this essentially the change of variables relating these momenta to the cross ratio and so on and so forth. So by explicit evaluation, one finds this residual dependence on the cross ratio. Now, Okay, let me pause if there's any questions about this, anything I said so far before going on to present these two main aspects of celestial 4-point scattering.
Let me ask a brief question. And this amplitude, the celestial amplitude, is directly related to a putative 4-point function of, let's say, operators in this quote unquote conformal theory?
Yeah, I mean, they're supposed to be, well, you're asking a great question. I don't
want to get into that, but
yeah, it is unobservable. I mean, so far, right, there is a one-to-one correspondence between bulk scattering amplitudes and celestial amplitudes. So one can think of the celestial amplitudes as the observables for this putative conformal field theory. So they have
then this delta of z minus z bar means what? This means the amplitude vanishes unless the 4 points are in a particular orientation?
Yes, exactly.
Yeah,
so this is a funny, this is a bit of an annoying feature of celestial 4-point. It only comes about in celestial massless 4-point scattering, actually. If one makes one of the external particles massive, then things become a bit more complicated, actually. And in fact, they haven't even been studied yet very much. But in this massless case, it's just the statement that you can think about the scattering plane somehow like crossing the celestial sphere on some circle. So it's a constraint that comes from the fact it's like a bulk point singularity sort of like constraint. You have to put points in the bulk particles meet at a particular point in the bulk, which means that on the celestial sphere, they have to be in a particular configuration.
But you don't, unlike the bulk point, you don't expect this to be lifted in a UV complete theory.
Yeah, okay. Yes, exactly. So this is going to always be here for any celestial mass. I agree, yes. Okay,
so thanks. Go ahead. I think I understand this. Go ahead.
Yeah, but this is a great question. Please do ask more.
Just a quick one. Did you already say what the central charge is supposed to be of this CFT?
So no, I cannot tell you what the central charge is, but so far we don't really have to, I mean, nothing from what I said so far. I mean, to get the central charge, one has to study operator product expansions amongst the two stress tensors, and actually that is quite a subtle problem. And so far, at least in the tree-level analysis that have been done so far, it's just a 0, but of course, there is, that problem about what the central charge is definitely not yet settled. But
and if you were to do what you're about to do for gravitons, would that settle it, or?
Yeah, in principle it would, if you yes. So the 4-point amplitude, well, but the question is, so far all we've done is to translate statements about, well, what we'll see in a moment is that we can translate certain statements about 4-point scattering into statements about celestial amplitudes, but even the 4-point graviton scattering amplitude, if you want to look, I think one would have to look to study loop amplitudes in gravity to be able to extract information about central charges and so on, and that may be a bit more challenging.
Sorry, but is there even a relation between gravitons as asymptotic states and stress tensor in this theory? You didn't tell us yet, right? What is the map between kind of particle quantum numbers and dimensions?
Look, as far there has been more work, which perhaps I have not completely understood yet, but there is one basic thing, namely the fact that the stress tensor is related to a subleading soft graviton. So it's a particular mode of a soft graviton. And to get the central charge Eva has been asking about, one would have to somehow compute a double soft limit in the bulk to subleading order. But one naive thing from the bulk point of view is that the subleading soft operator, the subleading soft factors are actually not just numbers, as in the leading case, they're operators, because they involve these omega d by the omega terms. And if you try to compute their commutator, they're not even going to commute. So it's not even, so for a long time, it was a bit confusing how one would take these OPE limits of these of two subleading soft gravitons to get something like a TT OPE from that. Now, from a celestial point of view, these ambiguities sort of go away because there is a way to actually just take two gravitons to be, there is a nicer notion of what it means to have a subleading soft graviton. So in particular, that on the celestial sphere, that just becomes the limit when you take the dimension of a graviton to take a particular value. And in particular, for the subleading gravitons, you have to take this dimension to go to 0. And the stress tensor is related to a shadow transform, actually, of this delta equal to 0 operator. But these shadow transforms are non-local transforms, and it's a bit subtle to understand. Like, you'd have to understand what the operator product expansion is of shadows of two local operators in some sense. And that's a bit, that's a problem which I think is still open. So it's not clear how to extract that from, or what exactly one should do to extract it.
Okay, that's all good. I'll just, but I mean, part of the reason it's confusing to me is just from the picture, you have these, ADS2s, if you want to foliate the upper quadrant of the picture.
ADS2?
ADS2s, I mean, hyperbolic spaces,
Those
right?
are these. I think you're using, if you're using this foliation with ADS3.
ADS3, sorry, ADS3s.
Okay.
Yeah, sorry. And those get larger and larger radius as you go into the future, right? And in ADS-CFT, the central charge has to do with the radius in Planck units, right? So so that's why it always seemed to me that it was hard to have a particular value of that, but that might be too naive in thinking about it too much like ADS-CFT, which maybe I should.
Right. That's interesting. Perhaps, yeah, that's one way to think about it. But I should also say that perhaps another way to think about it, which maybe would be more enlightening, may also be the flat space limit of ADS4, actually. So then the boundary theory is going to be like CFT3, and perhaps the celestial amplitudes are actually related via some sort of Mellin transform with perhaps Mellin correlators of the CFT3s. And maybe that may be a different way. Yeah, so of course, there's these 2 points of view that I think there is some connection. We think that there is some connection to either this ADS3 slicing or perhaps some flat space limit of ADS4. And all of this has to have some features of either, like usual CFT2 correlators or CFT3 correlators in some limits, but not much. I mean, it's not super well understood what these connections are.
Okay, no, thanks a lot. I realize this is an old question, so I should let you go on. Sorry.
Okay, it's great. Thank you. Okay, so let me just go on, and perhaps we can discuss later. So here, the first aspect I'm going to be focusing on is this beta dependence. So let's for now ignore this kinematic prefactor. So because this is fully determined, as I said, and let's just focus on just this scattering amplitude in Mellin space. So this is just one logarithmic Fourier transform with respect to the center of mass energy. And one simple question one can ask is, what do statements about 4-point bulk scattering amplitudes translate into on the celestial sphere? So the simplest thing one can consider is an amplitude that is just the power of the center of mass energy. So indeed, at low energies, the scattering amplitude will involve a bunch of terms like that. So there's going to be a linear combination of such terms. But let's just for a second look at one such term. Of course, this is not going to be a well-defined scattering amplitude because it's very, very badly behaved in the UV. But nevertheless, if one tries to compute the associated celestial amplitude, one observes that there is something really wrong about it, in that the Mellin transform itself is not even well defined unless beta plus p is imaginary, because one can do a change of variables here to put this into just the form of a Fourier transform of 1. And so one gets that the associated celestial amplitude is a delta function beta plus p, but for the restricted values of beta and p. So for general, for example, integer values of P, this is going to be badly divergent. So the first statement is that scattering amplitudes with poor UV behavior actually translate into badly behaved non-analytic celestial amplitudes. And conversely, if one perhaps a good set of observables for quantum gravity would be given by celestial amplitudes, which are well behaved and would automatically imply some nice properties about the bulk scattering amplitudes at high energies. Now, another example one can consider is the case of a tree-level scattering of, again, 4 massless scalars mediated by a massive exchange. So now this amplitude is better behaved in UV, right? At high energies, it just falls off as 1 over the center of mass energy, while at low energies, it just goes to a constant. And so plugging in this formula into this Mellon transform here, one finds using a contour integration that the celestial amplitude takes this form of 1 over sine pi beta divided by 2. So here, what we see is that a simple pole in S from the bulk point of view translates into an infinite sequence of poles in this beta variable. So in particular, there is an infinity of poles for all even integer beta. So this is quite funny. So let's have a closer look at how this comes about. So let's now consider bulk scattering amplitude, which at low energies is takes the standard form of a polynomial in S and T. And of course, one has to impose crossing symmetry properties and so on. But so let's consider this general case. So this translates into an expansion in powers of the center of mass energy, weighted by some function of this cross ratio. And so again, taking this formula and plugging it into the associated formula for the celestial amplitude, one finds that on the celestial sphere, one gets again a sequence of poles, but this time at negative even integer betas. So to arrive at this expression, one actually has to cut off these Mellon integrals at some energy scale beyond which this expansion will break down anyways. That's not a problem. Those contributions would be encoded in these dot dots, but they won't lead to any additional poles. So one can show that. But what's nice about this form is that we have a kind of a clean statement about the celestial amplitude as encoding information about the low energy effective field theory in the poles, in the residues of these poles in beta. So in particular, the first pole in beta, the one at the lowest negative, well, highest negative integer value, turns out to be determined by the lowest dimension operator in the low energy effective field theory. And the residue is in one-to-one correspondence with the coupling, so with the coefficient of that term appearing in the Lagrangian. And these other poles at increasingly negative values of beta actually are associated with increasingly with other terms in this low energy expansion of the amplitude, or equivalently, they're associated with increasingly higher dimension operators in the low energy effective field theory. So these terms in the Lagrangian. And as such, so these, from a bulk point of view, these have been studied by different methods, and they were shown to obey interesting positivity constraints. So here, what we see, because of this correspondence between these residues and these couplings from the bulk point of view, see that these residues were also going to be constrained. So they're going to obey interesting properties, which I should say that they should be explored.
Sorry to interrupt you so much,
Yes.
but let me just quickly ask something that's confusing me. I mean, these are poles and boost, which are the eigenstates, right?
They're poles in the scaling dimension. So this beta is the sum of the scaling dimensions of these 4 operators.
Okay,
So it's like it's the sum of Rindler, if you wish, is the sum of Rindler energies. four operators.
Okay, but the Rindler energies are eigenstates, or infinite sums of Minkowski eigenstates or momentum eigenstates, right?
Yes, that's right. That's right.
And yet you're saying one pole has to do with low energy operators in the bulk EFT, which would seem to be controlled by momentum expansion.
Yes, that's right.
So isn't that a little confusing, or should it be obvious, or is that why this is a
well, but from a momentum point of view, right? This is a polynomial. We're taking the Mellin transform takes care about, it's taking a linear combination of each of these terms independently, and this Mellin transform is the the thing that term by term leads to these poles. So there is still a one-to-one correspondence between. I'm not seeing. I mean, yeah, I'm not. You're still, this is, qualitatively is a bit different. There is still each term in the low energy expansion maps to a pole in beta, in other words. But the pole arises by actually integrating over all, like by putting each of the terms in a boost eigenstate instead.
Okay. I'll have to think about it more, but thank you.
Yeah, thank you. Maybe I'll also, yes, think about it. Okay, so now similarly, so here we saw an explanation. Yeah, so here we saw an explanation about half of these poles we saw appearing from just a simple pole in omega. So again, one can interpret them, these poles at negative integer, even integer beta, as arising from an expansion of this amplitude around small omega. But similarly, in a quantum field theory where the amplitude also admits an expansion around high energies, one can similarly run through the same arguments, but now writing down an expansion around high energies and then computing the associated Mellin transforms with a cutoff. And one finds, similarly to the previous case, a sequence of poles, but this time at positive even integer betas. So to put things together, here we have a sequence of poles everywhere on the real beta axis at even integers, because this amplitude admits both expansions around small energies as well as around high energies. Now, so another feature of celestial amplitudes is that also, so far I should have said that I was just focusing on amplitudes where massive loops have been integrated out and massless loops have been ignored. But one can actually account for loops coming from massless particles by generalizing these expansions, by dressing essentially each of these terms in the polynomial by these logarithms in the ratio between the center of mass energy and some UV scale. And so what one can see then is that loop corrections translate on the celestial sphere to higher order poles in beta. So this can be seen just by, again, just considering the Mellin transform of a power of the logarithm, which using some trick can be shown to translate. So for example, the rth power of the logarithm upon taking a Mellin transform is going to map onto r derivatives of a pole in beta, which gives a higher order, an order r+1 pole in beta at the end of the day. And so now we have celestial amplitude reorganizes also loop expansions in a qualitatively different way. So we have loop effects being captured by coefficients of these higher order poles in beta. And finally, what I want to point out about this analytic structure in beta is that also the UV behavior, so the high energy limit of the scattering amplitude actually has an imprint on celestial amplitudes as follows. So if one considers a limit where one takes the center of mass energy to be large for a fixed scattering angle, the amplitude in full theory of quantum gravity is expected to be exponentially suppressed due to black hole creation. And so on the celestial sphere, there is a way to extract to actually localize the Snellen integral onto this high energy behavior, namely by taking the limit as this beta parameter becomes large. So in this case, the integral just localizes onto the high energy regime, and one finds that the celestial amplitude is going to behave for this naive high energy behavior of the bulk scattering amplitude as an Euler gamma function of beta divided by 2. So the only take-home message here is that this gamma function actually does not have any poles on the positive real beta axis. So it still has poles on the negative beta axis, but it's free of poles on the positive beta axis, which is a qualitative difference between scattering in usual quantum field theory, where we expect expansions around high energy to also be allowed, and quantum gravity, where we expect this exponential suppression coming from black hole creation. So, okay, so now I still have, I guess I'm almost running out of time, so I'm going to be very quick in the second
you
part.
started like at least 5 minutes late, so maybe you have
yeah, but in any case, since I'm done with this beta structure before showing you a little bit about this analytic structure in Z, perhaps if there's any questions, urgent questions.
Yeah, maybe I wanted to ask, so what is known about like the spectrum of the CFT? So how many operators? It's probably a continuum spectrum, but is there any constraints on which operators?
I can show what some elements of this, and maybe we can revisit your question afterwards.
Okay.
So this is what I'm about to say. Like now, so far we have just seen some features of celestial amplitudes as functions of beta, but of course there is this other dependence as a function of the cross ratio, and that's also interesting to study. And as Victor is saying, it's you know, that piece of the amplitude is expected to encode some information about the spectrum of the theory. So how does that come about? So let's consider the simplest example. So you can ask me later why we're actually considering now the T-channel exchange from a bulk point of view, but let's just focus on that one, just because it turns out to just have to give rise to the simplest possible celestial amplitude. So let's start from this. We perform a Mellin transform, and it turns out that the celestial amplitude in this case, as we said before, will take the form of a conformally covariant factor, which now I'm rewriting because we're interested in studying the OP limit of as 1 goes close to 3. So it's convenient to, instead of using the conformally covariant prefactor, which is symmetric under exchange of all 4 points, to be using the one that is only symmetric under exchanges of pairs of points, which just differs from that by just a function of the cross ratio, which is why we see here that there is, previously I said, okay, that the leftover piece just depends on beta. The reason why this leftover piece here depends on H13 and H24, which are the differences in the weights of the external operators. The reason why that is because we're just stripping off a different conformally covariant prefactor. So what we want to focus on now is this function of the cross ratio and try to decompose it into conformal blocks. And why would one do this? Because it's well known that in usual conformal field theory, these expansions of conformal correlators encode information about the spectrum and the OP coefficients of the theory. So it's by far not obvious that the same thing should apply here, in particular because of this delta function in Z minus Z bar, which is very uncharacteristic of usual conformal field theory. So this we won't usually encounter in usual examples of conformal correlation functions. But nevertheless, it turns out that one can do a conformal block decomposition of this function. And the way we're going to go about it is by treating Z and Z bar as real independent variables. So this is equivalent to thinking about the celestial sphere as becoming Lorentzian, and then decomposing this function into on a complete set of solutions to the 2-particle conformal Casimir operator over the Lorentzian square. So why the Lorentzian square? Well, I should say that actually this amplitude is, for this particular kinematic configuration we're considering, where we have particles 1, 2 incoming and 3, 4 outgoing, it turns out that in the set of conventions I've been using, the conformally covariant cross ratio is actually restricted to lie in this interval 0, 1, and it's vanishing everywhere else. So it's convenient to just try to decompose this on a complete set on this particular region where the amplitude is non-vanishing and sort of see what happens. So fortunately for us, this problem had somewhat been studied by these people here, just in usual conformal field theory. And so the idea is that it's well known that the conformal Casimir equation on 2 particles, so here 1 and 3, actually takes the form of a differential equation, which is just a hypergeometric equation. And it has a bunch of a set of solutions, which can be made into a set of orthogonal and complete solutions, which are called conformal partial waves. So these are different from the usual conformal blocks in that they obey these orthogonality and completeness relations. And they are in fact linear combinations of the 2 solutions. This is second order differential equation. So it has 2 solutions, which are typically called the conformal block and its shadow. So the full conformal partial waves associated with global conformal symmetry in 2 dimensions for this Lorentzian case I'm considering have been shown to, well, one version of them can be taken to factorize into independent conformal partial waves for SL2R instead. And these conformal blocks have been written down before. They're related to these F21 hypergeometric functions. So this is just some formalism which has been worked out before. And the main take-home message here is that these conformal partial waves actually form an orthogonal and complete set of solutions to this conformal Casimir equation. This is going to be important because it's going to allow us to decompose not just our celestial amplitude, but any function of this conformally invariant cross ratio Z in this basis. So one can, independent of questions about spectrum or OPE, one can do this exercise. So here is what we're going to do. So we have our celestial amplitude, and it can be written in as an integral, as a linear combination of these conformal partial waves with some coefficients to be determined. So the hard part here is to determine these coefficients. But fortunately, since these partial waves are orthogonal, one can extract information about these coefficients by computing the inner product of the left-hand side, which is our celestial amplitude, with these conformal partial waves. And so this can be done, and one gets some answers, which in this case are simplified because of this form of the celestial amplitude. It turns out to be very convenient and easy to evaluate. And it actually, this G of H and H bar localizes into a sum of 2 delta functions in H plus and minus H bar, which allows us to just evaluate one of the integrals. And then the other integral, one can deform the contour in this complex remaining H plane to pick up the poles in the remaining integrand. And so upon doing that and being careful about accounting for the poles coming from both the coefficients and these partial waves, one finds that the celestial amplitude takes the following form. So there's 2 contributions here. One of them is can be seen to be a discrete to include an infinite number of exchanges at dimension 1 plus n and spin equal to 0, while the other one involves a continuum of exchanges of delta equal to 1 and imaginary spin. So let's take a closer look at what these are. So if we look at the first term, we also see that, perhaps surprisingly, because as far as I understand, there was no reason why a priori the celestial amplitude should have this nice property that the coefficients factorize. we see that the coefficients actually do factorize, and moreover, they correspond to 3-point coefficients appearing in the celestial amplitude of 2 massless and 1 massive particle. So these had been computed before, and they're known to be proportional to these Euler beta functions with these arguments. And this d factor here is just a normalization of the 2-point function, which is fixed by Poincaré invariance, and again, can be shown to take this form. So up to these finite trigonometric functions, this first term, it looks exactly like what one would expect for a series of massive exchanges, actually, of dimension 1 plus n and spin equal to 0. Now, the second term is perhaps more confusing. So we have this continuum of exchanges, but again, the coefficients factorize, and they turn out to be exactly the same as the coefficients appearing as the 3-point functions of two massless scalars and the light transform of a massive particle. So the light transform, what it essentially does is it generates a factor of inverse Euler beta function in those arguments, such that it just takes this form. And then again, this d function here is the 2-point function of 2 light ray transforms of massive scalars. So we see that the second term is essentially it's the light ray counterpart of the first term. So here we have again the light transform, I should say, is an integral transform that turns a conformal primary operator into another conformal primary operator with dimensions, if the original dimension was delta, or weights, dimension and spin were delta and j, the light transform turns delta into 1 minus j and j into 1 minus delta. So here, since original j was 0, we have delta equal to 1. And since original delta was 1 plus n, here we get, the original, I should say that these are light transforms of massive operators on the principal series. So the dimensions here, actually, the spins are just 1 plus I lambda, which correspond to 1 minus delta, where delta is 1 plus I lambda. So this is actually a series of massive scalar light transforms of massive scalars lying on the principal series, and not of dimensions, not of integer dimensions, because as we can see, there is a continuum of such exchanges here. So this formula can also be, I should say that we've done a couple of checks on this. Namely, one can show that for z different than z bar, these two contributions actually precisely cancel, which is what would be expected, because for z different than z bar, we can see that this amplitude actually vanishes. And one can also look at the small z and z bar expansion of these two terms and actually see how this delta function in z minus z bar arises from this second term. So everything, this formula seems to be correct. So, okay, so now I'm actually at the end. So let me just summarize what I tried to say today. So the main thing we studied was the general structure of a celestial amplitude of 4 massless scalars. And we saw on the one hand, we saw that these celestial amplitudes have an interesting structure as functions of this beta parameter, which we defined to be the sum of the external dimensions of the operators in the celestial sphere. And so in particular, we saw that we get a sequence of poles where poles at negative beta encode information about low energy data from a bulk point of view, while the analytic structure for positive real beta is drastically different in quantum field theory and quantum gravity. So in particular, in theories where black hole production is allowed, one will not see any poles on the positive real beta axis, and moreover, I mean, more generally on the right-hand complex beta plane. Now, we also saw that the residues of these poles are actually functions of this conformally covariant ratio Z. And in one particular case, namely in the case where the coefficient, where we look at the pole with residue equal to 1, this coefficient actually turns out to have a nice conformal block decomposition that factorizes and indicates that that the scattering of 4 massless scalars is actually on the celestial sphere has to be mediated by a massive particle. And in particular, there is an infinite number of such exchanges of massive particles, which with positive integer dimensions. As implied, actually, we suspect that this infinite sum actually arises from Poincare symmetry. So we know that translations actually shift the dimensions of these operators by 1. So this discrete tower is suspected to arise from translation invariance, while there is also a continuum of terms, which can be interpreted as light ray transform of these massive scalars, which are responsible for this delta function in Z minus Z bar. So there are a lot of open questions. So here I just, in this conformal block decomposition, we just looked at one particular residue, so the one associated with the T-channel exchange from the bulk point of view. But there is an infinity of such residues, which are polynomials in Z. So one could ask the question, okay, what about their conformal block decomposition and how do they encode information about the spectrum? Now, another question is that from the bulk point of view, we know that these coefficients also encode a wealth of positivity constraints. But on the other hand, here we're working, these from a bulk point of view, these positivity constraints can be obtained via dispersion relations, which are naturally, can be written down at high energy. So they depend on the behavior of the scattering amplitude at high energy and fixed momentum transfer. But here in the celestial amplitude, we are keeping the cross ratio fixed, which is equivalent to keeping the scattering angle fixed. So in some sense, celestial amplitudes capture a different regime, a different regime to the one in which dispersion relations can be written down. So it may be interesting to study whether one can derive new positivity constraints governing these coefficients by generalizing, by writing down analog, perhaps dispersion relations on the celestial sphere. Then I should have also pointed out that in this conformal block decomposition I've written down, it looked like the for equal external dimensions, the coefficients of the conformal blocks appear to be positive, and it would be, of course, very interesting to study whether one can formulate a bootstrap problem for the celestial CFT. And to conclude, well, there is many things we still have to understand. We need to understand better how the celestial amplitude behaves asymptotically for large beta. Because again, this will be something that may be related to formulating things like dispersion relations on the celestial sphere. And finally, to touch on some question I posed at the beginning. So can we use the celestial amplitudes to say something new about scattering in quantum gravity? Perhaps we have a little bit of evidence that perhaps the answer is yes, in that if one knows if one knows the analytic structure in beta, so in particular, if one knows all of the poles in beta, as well as the spectrum of the theory and the OP coefficients, which we saw that they could determine these residues in beta, then one can reconstruct the scattering amplitude just from this data. So that would be a very interesting question to explore. So with that, thank you very much, and I'm happy to take any questions.
Yeah, thanks. Let's thank Anna. And I mean, as usual, we're a bit over time, so whoever needs to go should feel free to go, but then whoever has more questions should feel free to ask.
I have a question about the analytic structure in the beta plane. I'm used to scattering amplitudes and momentum spaces having all kinds of complicated things away from tree level, branch cuts and stuff. Do you know information about on general grounds what the analytic structure in the beta plane should be?
So here it looks like, as I said, I mean, the loops seem to just translate into higher order poles in beta. So from that point of view, it looks like really, okay, except for cases where one has condensations of these poles in beta, which I believe we thought about that a little bit. And there are some situations in quantum field theory where one may expect to get branch cuts in beta, but we believe that in quantum gravity, actually the analytic structure is going to be very nice. So this cannot.
But I mean, so some massive particle production threshold will turn that'll turn into poles in beta? In an ordinary scattering amplitude, you have some thresholds whenever you can create massive particles or something.
Yeah, that's right. That would correspond to loop amplitude. Yes. Oh.
Not massless loops, though.
Right. Massive loops. I see what you're saying. Well, yes, because here we studied, we worked in this perspective that, we have some energy scale and we have integrated out. So these massive loops are talking about actually translated into some effective interactions in the low energy effective field theory. So yeah, we haven't really studied the full case where one is above scale, but nevertheless, the information, so it's not right from an effective field theory point of view, right? These coefficients of these lower dimensional operators actually do encode the information.
Well, maybe.
In a complicated, yes. But
I mean, usually that's like flowing backwards up a renormalization group trajectory. That's a tricky business.
Right.
So, well, it would be interesting if you could establish on general grounds that, the function is meromorphic. That would be amazing. I mean, scattering amplitudes for general outside of perturbation theory things are complicated beasts. If you could argue that this presentation makes the thing a meromorphic function, that would be spectacular.
I agree with you. Yes, that would be very, very interesting. And perhaps, yeah, I mean, certainly one would have to think a lot more about this. I mean, there is many more examples one can study. So I should say that, yeah, we only looked at very basic features here. But I agree, yes, it's a very interesting question. What is the analytic structure in beta, and what can we say about, how much can we say about? To what extent do these poles and higher order poles in beta determine the scattering amplitude? So of course, if there is extra stuff, like you're saying, like branch cuts and other weird things happening, then of course, this question is going to get blurred by that. So it's obviously a very interesting question.
And maybe you'd argue that there are no absolutely stable massive particles. I don't know if we believe that, but we probably don't. But, so maybe then everything is resonances. I don't know what the right thing is. Okay, let me just raise the question.
The question about resonances, I think, is still interesting because, okay, there's been this discussion, and I think Nima is saying this in when he gives the talk on the subject. I mean, resonances in this formalism, I mean, they still make it to the celestial sphere. So one can even put massive particles in a conformal primary basis. And there is all sorts of things that are not really understood about that. But nevertheless, massive particles make it all the way to the celestial sphere. So in some sense, perhaps they can be thought of as states in the conformal field theory, in the celestial conformal field theory. But we have, people have not really thought about this yet.
Okay, thanks for the answer.
And I should say that an even more basic question is literally, what are the analog statements of what I'm saying for when you have massive external states even? What I've been saying is just not going to be the same. I mean, it's going to be way more complicated. But nevertheless, I mean, one could still study, you know, in principle, the analytic structure of 4-point scattering. In fact, to some extent, I'm working on this now. So trying to kind of generalize the statements for the case of, you know, simplest case of 3 massless and 1 massive particles. So what happens in that case? What are the analog statements in that case? So that has not been done yet, for example.
Okay, thanks.
So maybe you said that, but I missed. If you just for like if you have external particle of mass m and spin j, then how many operators do you need to parameterize that? Just for external states, what is the map between?
For massive, yeah, I haven't said anything about massive particles because it's a bit more complicated. But so essentially, what happens is that this Mellin transform, which puts a massless particle in a conformal primary basis, actually gets generalized to an integral over a bulk to boundary propagator on these ADS slices, which sort of slice the future and past of the light cones. So in other words, to put a massive particle in a conformal primary basis, one has to carefully work out what these so-called massive conformal primary wave functions are, or these bulk to boundary propagators are. And to some extent, this problem has been addressed in some series of papers by Lyons-Lanikov. So they have written down these Green's functions, these bulk to boundary propagators for arbitrary spins and
so what is the outcome? What kind of operators do you get on the celestial sphere?
It hasn't been studied. I mean, what kind of operator? You're going to get an amplitude that still will transform like a conformal, you know, it will transform nicely under global conformal transformations. But so far, that's all we know. I mean, like people haven't really been studying these things because it actually, even in this very simplest example I'm talking about, you know, it becomes very complicated because you have to take now, you don't just have like 4 Mellin transforms and you saturate, you know, the momentum conserving delta function, but you have each integral against this bulk to boundary propagator is actually a 3-dimensional integral over an on-shell massive momentum. So it's like, oh, sorry, I think you're frozen, or am I frozen? I'm not sure.
I think it's Victor.
Okay. Maybe I should wait for him to get back.
Just a naive question. How did you put massive particle at non-infinity?
So yeah, that's what I'm saying. So one uses, it would be nice if I could draw, but okay, I can connect. I have to connect the iPad. So the idea is that you can take Minkowski space. Sorry, maybe I can go back to one of these slides. So here, more or less what's happening is that you can slice Minkowski space in the usual way with Rindler and Milne regions. And these Milne regions then can be sort of sliced, I don't want to say foliated, but sliced with ADS3 slices. And then the common boundary of all those slices is going to be the celestial sphere. And what one can do is, so in particular, why should one do that? Well, one does that to resolve. So we know that massive particles actually go to infinity, like make it to future time like infinity. So one can resolve future time like infinity with this with one of these ADS3 slices, and then a massive particle with a certain asymptotic momentum is going to be in one-to-one correspondence with a point on this ADS3 on this hyperboloid, which resolves I plus. And then what one can do is one can map that point to the celestial sphere by integrating against the associated bulk to boundary propagator. So this is how one arrives at the formula for it.
I see. Thank you.
In this conformal block decomposition, are these the things appearing? Are they the principal series and discrete series, like unitary representations of SL2C? And is there?
That's a great question. So this is equivalent to it. This is just a light transform of the unitary principal series, right? It's that. So it's related to that. And this, I know that there is this discrete series representation. I'm not sure if it's exactly that, but could be. I don't know.
Yeah, I mean, more generally in this, do you expect this decomposition? Do you expect this SL2C action to be unitary? Is there some inner product with an appropriate definition of hermiticity that
that's a
you'd expect to be unitary, like, or some reason why you would expect only unitary things to appear?
No, it's a great question. It's not obvious. No, it's not obvious why I wouldn't expect that. And but I don't really have much more to say about this. I don't fully understand. Like, we don't really understand how, like, unitary, like, this conformal field theory is certainly not even unitary. So because it has all of these negative dimension operators, but somehow magically here, all of the operators that appear, there's no negative dimension things.
Yeah, well, it's certainly not unitary of the same like usually we have L1 dagger is L-1. So it's certainly not unitary with that hermiticity relation, but it might be unitary with L1 dagger equals L1 and L-1 dagger equals L-1.
Yes, but let me say also that Andy and collaborators have a paper where they use a shadow. They replace the usual Klein-Gordon inner product by a shadow inner product. So essentially what they do is the dagger actually gets replaced, or rather the complex conjugation. I don't remember. So the dagger essentially more or less gets replaced by a shadow. And if you consider this shadow inner product, what they show is that actually, like, the hermiticity properties with respect to the shadow inner product of these L's are actually the same as one would expect in a conformal field theory. So perhaps, but that has been done at the level of 2-point functions, but like how one is supposed to implement that in computing hard point functions, and in particular conformal block decompositions, like that, has not been done or really understood. So the role of shadow, there seems to be some, but we don't really understand.
Perhaps a more general sort of question that I don't know, be interested in any comments you have. Clearly, you're getting a lot of mileage, I think, already from just it's a kinematic reorganization of the S matrix and a different language you're expressing it in. Mm-hmm. But it's whether I'm wondering what signs, if you feel like there are any signs that it's really like holography, like, ADS-CFT, the power of it isn't that it's a kinematic reorganization into boundary variables. It's the fact that the dynamics is a local quantum field theory on the boundary variables. Whereas here, it's clearly not an ordinary local quantum field theory. Is there any sign that it's more than a kinematic reorganization?
I totally agree with you, but these OPEs, which we and other people have computed, at least in some sector, like for example, for MHV scattering amplitudes, it really looks like a local OPE. So people, Banerjee and collaborators were able to actually like reconstruct essentially all MHV scattering amplitudes from OPE data, which is quite, well, not quite, because there is the subtlety about like SL2R left and SL2R right, and one has to restrict, there is some subtlety there. So we're not quite, not even the MHV amplitudes fully have been reconstructed from this OP structure, but certain pieces of that have actually been argued to actually come from local OPs. So there is some evidence that perhaps, more generally, it looks like perhaps self-dual gravity could have a description in terms of local or kind of, at least celestial conformal field theory. So we don't know whether in general, it's going to be as powerful as ADS-CFT is, but certain, at least some sectors, for example, of gravity, perhaps could have. There is some evidence that at least some sectors could have such a description. And in particular, so if you just look at soft sectors, those certainly do seem to have such a structure as well. So like the theory that would sort of reproduce bulk scattering amplitudes with low energy particles. So like low energy radiation and stuff like that.
But then, like, you would, and if you
You're
try
back.
to,
Yes, sorry. I'm not sure how much
yeah, at some point I got disconnected, but okay, I mean, I think I do not know what you said next, but there is no need to repeat for me because I was disconnected for a few minutes.
Well, I'm not sure where you.
But no, but I mean, in general, I mean, I guess I keep wondering what is the spectrum. Yeah, say if you want to, we dream of like having a CFT that some theory that also describes this exchange that you have on this slide, that what it should have this continuous spin operators as some sort of part of its spectrum.
It looks like one needs this. It seems like, at least in these cases, and it seems like in all 4-point massless scattering examples, there's going to be this delta function in Z minus Z bar. And it really looks like in order to be able to get that back from a conformal block decomposition like thing, you really need to have a continuum. Otherwise, for a while,
like continuum of spin, right? Not continuum. So indeed, like some sort of something like this light ray. Is this light transform related to light ray operators?
Yes. It seems. I mean, it is. This is how we got, in fact, this coefficient by actually performing a light transform of these massive particles. But let me also say that here we used this Lorentzian sort of like formalism. So we really think about Z and Z bar as real independent variables. I mean, otherwise in Euclidean theories, you wouldn't even expect to have such contributions. Now, one could ask, okay, what happens in Euclidean signature? Because then, you'd have to expand on a slightly different set of conformal partial waves, and this decomposition presumably is going to look different. But I mean, yes, there's going to be there may be a sense, in fact, to some extent, in a different kinematic regime, a conformal block decomposition has been done by a group at Brown. So Volovich and collaborators, they have done this decomposition in Euclidean signature, and they found that in some examples they considered, it looked like you have a bunch of well, I need to remember what exactly, but they had an infinite sum over all integer spins instead of having this continuum of spins in what they did. So, but in their analysis, it was less obvious, like the coefficients appearing in these decompositions, they are not clearly related to 3-point functions, for example. So there is a puzzle. If you try to do, I should also say that if you try to do a decomposition of the S channel amplitude in the corresponding, conformal partial waves, which would be associated to the corresponding OPE, then what you'd find is that the coefficients here look much more complicated. So in fact, they turn out to just be generalized hypergeometric functions, and it's much the connection between that and 3-point coefficients is really less clear. And to some extent, this problem has also been addressed by Stieberger, Taylor, and collaborators, where they took sort of a different point of view, that instead of looking at these 4-point functions with this delta function singularity in them, they took a shadow transform of one of the external particles, which smoothed and sort of like removed this delta function, and then did a conformal block decomposition of that. And then after making it single valued via some prescription, which apparently is also done in minimal models or whatever, I don't know, like they were able to kind of remove a term from there and kind of take the shadow transform back. And at the end of the day, they found some conformal block decomposition, which had really nice properties. But that's also very recent work. And I mean, I don't think we fully understand like why that sort of works and why that gives the result. I mean, I think it would be a very interesting question to understand under what, I mean, in conformal field theory, we know that conformal 4-point functions right, have this nice factorize. It's a very non-trivial property that if you do a conformal block decomposition of a function of a cross ratio, the coefficients will factorize. Conformal field theory that comes about because there is a local OPE. So that implies this magical property. But here, of course, we don't know in general if there is, I mean, an OPE, but doing this decomposition and studying their properties perhaps will tell us something about the structure of the general OP. Let me also make one other comment, namely that, again, I think there is a relationship between celestial amplitudes and flat space limits of CFT3 Mellin correlators. And perhaps what one should try to do is also maybe try to understand these decompositions via that sort of Mellin approach for conformal correlation functions. I mean, the relationship is not obvious at all, but
you know how Virasore arises? Because you start from some CFT3, right? It has no Virasore.
Yeah, I mean, it's a great question. I mean, yes, no, that's a great question. I don't know how that comes about, but it hasn't also been like, I think, yeah. I'm just saying a statement that, I mean, this should be, I mean, we know that scattering amplitudes can be obtained as flat space limits of CFT3 correlators. So to some extent, again, I'm also working on this, partly on this, like you can translate this statement into a statement about relating celestial amplitudes to flat space limit of Mellin correlators, but much more, I mean, I understand what the relationship is, but we haven't really like been able to use this to say, well, so far it's very recent. I mean, it's very recent work in progress, actually. Yeah. There are many things one could try to explore, and this thing you're asking, yes, that's a great question, but we don't know. I don't know actually what the
sorry, I had to step away for like 10-15 minutes. So I'm sorry if somebody already asked this, but I wanted to just ask you to make a few comments on the Regge limit instead of the hard scattering limit. So I guess since your S and T were both proportional to omega square, just the starting point didn't have the Regge limit as a nice sort of built into taking the omega integral.
No, it's not. I mean, we don't really know how to keep, like naturally when we do this Mellin transform, I mean, this is a great question. Naturally, when we do this Mellin transform, let's see, where is it? Here,
omega integral.
We're not keeping, like one naturally keeps T divided by S fixed, right? We're not keeping T fixed, you know, T is not fixed. But on the other hand, perhaps one can somehow reach the Regge limit, as I was saying. You see, if you take T divided by S to 0, that would be the Regge limit. And that corresponds in this definition, like the limit as Z goes to 0. Right. But these limits, it's not obvious that they would commute, right? Keeping T fixed and taking S to infinity versus you're approaching things in different ways, but nevertheless, maybe there is a way in which one can extract. But I would say, I mean, I expect it to be related to a small z limit of the celestial amplitude somehow.
The reason, of course, I'm asking is that there are papers by Minwala and his group and other people who even proving some kind of boundedness in the Regge limit. It's smaller than S squared. So one natural question what wonder is that what does that imply for the celestial CFT?
I agree. It's a great question. I don't think it's been
okay, thank you.
It would be interesting to study. I agree. But one would first have to understand how to take the Regge limit on the celestial.
Yeah, I agree. I hadn't looked at these formulas before, but I realized that the way the omega integral is done kind of makes it hard, just naively.
Okay, any other questions, comments? No, then, whoever's left can thank Anna again. Call today.
I'll stop the recording.